Okay, so let's say you're a contestant on a game show and you have three doors in front of you. Let's call them door number one, door number two, and door number three. And behind one of these doors lies a cash prize. The aim of the game is that the game show host gives you one chance to pick one door, and if you pick a door where the cash prize is behind that door, then you win that prize. If you pick a door that is empty, then you leave to go home empty-handed. Simple as that. One thing these doors represent are unbiased sets, and what that means is there's an equal probability of the cash prize being behind each door. Effectively, that means you have a 1 in 3 chance of getting it right and getting the door which contains the cash prize. However, if that was the game show, then that would be pretty boring because you have more chance of losing than winning. You have a 33% chance of getting the right door. So there's a bit of a twist with this sort of game show, and that is when it comes to choosing, the host, let's say for example you chose door number one, the host will then, before revealing what's behind door number one, he will look at the other two doors, door number two and door number three, and he will open a door which is empty. So of course he knows what's behind each door, and he opens an empty door. Let's say in this instance he's opened door number two, and now he gives you a choice. He lets you stick to your original choice of door number one, or lets you move over to door number three. What would you do? Would you stick to your choice, or would you swap and decide to open door number three instead? I'll give you 5 seconds to think about that. Well, intuitively, you may think that you've still got the same chance of winning whichever door you pick. So you may think that you've got a 1 in 2 chance now of winning the prize in door number one or door number three. So it probably doesn't make a difference, and you may decide to stick. However, you may be fascinated to know that if you do decide to change your answer from door number one to door number three, then you are twice as likely to win than if you stuck to your original choice. And this is known as the famous Monty Hall problem. The Monty Hall problem is usually depicted with a star prize of a car and a booby prize of goats. Don't know why, for some reason, but what this problem does show is the idea of conditional probability. The very fact that the host gives you, he opens a door which is empty, has changed around the probabilities such that choosing or changing your answer to the other door gives you a twice as likely chance of winning. Let me show you this. So we had this before, we had a 1 in 3 chance of winning from each door. We chose door number one, so the chance of winning here is 1 in 3, and so the chance of winning from either 2 or 3 would be 2 in 3. Since he's opened door number 2, that probability has transferred over now to just door number 3. Your probability remains the same, but the 2 in 3 chance is now in door number 3. So you should always change your answer. This is a very simple way of looking at it. Probably a more effective way is to analyze it differently, and that is by looking at each scenario. So let's do that quickly. Let's say you had the 3 doors and the cash prize was behind door number 1. So you pick door number 1 as before, and now the game show host will either open door number 2 or door number 3, because of course these doors are empty. And so what you have is that in this case, if you decide to switch or swap your door to one of the other doors, then of course you would lose because the cash prize is in door number 1. You would win if you stick. So in this case, you don't want to swap, you want to stick. If the cash prize was behind door number 2, then the fact that you chose door number 1 will mean that the game show host will open door number 3, as this is the empty door. So in this case, if you did decide to swap, you'd choose door number 2 and you would win. If you stuck to your original answer, then you would lose. Finally, let's have the scenario of the cash prize being behind door number 3 and you chose door number 1. So similarly as before, there's only one other door which the host can open. That will be door number 2, as this is empty. And if you decide to swap, you'd be correct because the cash prize is behind door number 3. If you decide to stick, then you would lose. So this is very similar to having a probability tree when you look at the last column. And with the 3 scenarios, you pretty much have 3 outcomes. And in 2 out of the 3 outcomes, you can see that you would win if you decide to change your answer. So you have a 2 in 3 chance of winning and 1 in 3 chance of winning if you decide to stick. 2 in 3 chance of winning if you decide to swap, as we saw before. And this is the famous Monty Hall problem.